we're going to be looking at a special topic in generative models, which is going to be discreteness. Again, this is part of my final set of lectures on several special topics in generative models. So we had a topic on evaluation, a topic on combining variants of generative models, and today is going to be on the issue of discreteness in generative models. So why is discreteness interesting, and why does it merit its own lecture? In a lot of the data that we're working with, we have inherently this aspect of discreteness. So, for example, if you're working with certain types of data like graphs or DNA sequences, text, source code, representations of molecules, this data is often really different from the data that the type of data that I've been using as my running example throughout the course, which have mostly been images. And if you want to model these kinds of data, there's going to be some special issues that you will have to worry about. And that's some of the things that I want to talk about in this lecture. So that's one reason why discreteness is interesting. Another that might be a little bit less obvious, but equally important, is the fact that many latent representations that we would like to learn could also be inherently discrete. Right? So these two bullet points refer to two types of generative modeling problems that we've encountered in the course: generation and representational learning. In representational learning, discreteness might refer to the fact that you want to learn some kind of discrete binary concept, such as, let's say, gender, or some kind of latent parse tree that explains the object that you're modeling. Or you might want to compress your image into, or compress your input into a discrete latent code. So you might want to do compression, which has to be inherently discretized. So in many cases, also these representations make more sense when they're discrete as opposed to continuous. And so in this lecture, we're going to look at general algorithms for dealing with discrete data, both in latent space and in observed object space. So both in the space of X and Z. And the plan is that, first of all, I want to spend a little bit of time defining what the problem of discrete generative modeling is. And then we will talk about two important techniques in generative modeling that are useful for solving any sort of discrete optimization problem that you might have. One of them is going to be reinforce. I alluded to reinforce in our first lecture on VEs, but we're going to talk about it in a little bit more detail. I haven't mentioned some important techniques that are needed to get reinforce working in practice. There's going to be one topic of today's lecture, and then I will talk about another technique called relaxed reparametrization, or you may have heard of the Gonval softmax trick if you've been reading a little bit on these. So this is going to be another approach that solves essentially the same problem as reinforce, but in many cases it can give you improved performance. So the other part of the lecture will be on this technique. And I know that some of you are working with discrete projects. I know there's a project on generating text using, I guess, either GANs or some kind of reinforcement learning type of models. So these approaches, I think, will potentially be really useful, or at least being aware of this problem and being aware of these techniques will be really useful for any projects that you're working on that involve discrete data, either in input space or in latent space. Okay, so that's the plan. So as I said, let's first start by defining what is the problem of discrete optimization or discrete modeling. For the purposes of this class, the problem of optimizing over discrete data, or the problem of discrete modeling, will be given by this equation. So here I am trying to optimize an objective which consists of an expected value. And in this expected value, I have a parameterized model, which is a probability, and we're trying to take expectations relative to this probability. So here Q of phi is some kind of model. It's a function of some variable Z, and I want to take expectations of, I want to optimize the expectation of some function under the model, but the model is itself parameterized by parameters phi, and I want to maximize phi. So why is this interesting, and why is this potentially hard? So we actually saw one example of a problem of this form, and this was the elbow of a VE. If you have the elbow of a VE, remember this is the formula, right? This is exactly what the elbow is. And here we have an expected value relative to Q, which is our approximate posterior. And then the integrand, or the thing of which we're taking the expected value, is a function of both z and x. And our goal is to optimize the elbow, or at least in standard variational inference, our goal is to optimize this elbow over two sets of parameters, the parameters theta of the model, which live here, and then the parameters phi of Q. This is the problem that we tried to solve when we did variational inference, and it's clearly an instance of the above formula. And if you remember, this was not completely trivial to solve when we first studied this problem. As I said, there are two sets of gradients, there are two sets of parameters here, and each of them has their own gradient. And the gradient with respect to the first set of parameters, theta, is easy. That's because if we were to take the gradient of this relative to theta, well, we can flip the expected value and the gradient, so I can put the gradient inside the expected value, and now I have an expression that's the expected value of a gradient, or it's the expected value of something, and I can always approximate expected values using Monte Carlo. So when we took the gradient with respect to theta, that was easy. We just put the gradient inside the x, and we applied Monte Carlo. Now, and this is of course the formula that I just showed you. So we do this, and then we approximate the expected value using gradients. That's exactly what I just drew on the board. But if we want to take gradients with respect to the other set of parameters, phi, then this was not immediately trivial. When z is continuous, we saw one way of doing this using the reparametrization trick. So we reparameterized Q, and as a result, we obtain a formula that's similar to the one you see here. It's a formula that we can easily approximate using Monte Carlo, and then we can flip the order of the gradient operator and the expectation operator. Because again, the problem here is that now that we're trying to compute the gradient with respect to phi, now we can't just flip the order of the expected value and the gradient operator, because my gradient is with respect to the distribution according to which I'm taking the expectation. So now this change of order of the two operator doesn't work anymore. And as a result, we saw two ways of dealing with this problem. One was a first version of the reinforced estimator, and then we saw an even better way of doing it, which is applying the reparametrization trick. So this is what we did with the elbow, and my high-level point here is that there are many instances of this problem in generative modeling, and oftentimes it is not completely straightforward to solve this optimization problem. So in the first part of this lecture, I want to look at the reinforced estimator again and show you how it can be a general technique for solving optimization problems of this form. So let's first quickly look at this. Let's first quickly remember what this trick was when we first introduced it. just before we do this, I want to mention a few more applications of this identity. So in the context of an elbow, we could use the reparametrization trick, but sometimes it's inapplicable. Why would it be completely inapplicable? Well, I guess there's two scenarios. One scenario is that sometimes the z that we're trying to model could be discrete. That could be the case of a discrete latent variable inside a latent variable model. Then we just cannot apply the reparametrization trick. So a discrete VE, a VE with discrete latent variables now can no longer be solved using the reparametrization trick. You might not even call this a VE anymore. So we need a specialized method. And also, there could be other instances of this problem where Z is discrete. I'll mention an example where we're talking about generating some kind of objects which are discrete, right? So this Q here could also be some kind of generator, and we're trying to maximize the score of some set of generations. For example, well, the example that I will mention in a moment would be something like a discrete GAN. Let's say we want to apply GANs, but the things that we're generating are discrete, and we want to maximize the score. We want to, I guess, minimize the score of the discriminator under our samples. Then F can be seen as the score of the discriminator, and we want to optimize parameters phi such that this score is bad. Then this is, again, another instance of this problem where F is non-differentiable because it is a function of a discrete variable. And also F could be non-differentiable in the sense that, let's say that we're generating some kind of text, but instead of maximizing the likelihood of that text, we're maximizing some kind of downstream non-differentiable score. So for example, there's a lot of automated metrics in natural language processing. Their names are typically the names of colors. They're called the blue metric, the rouge metric. For some reason, it's always, there's a mauve metric. For some reason, it's always a French color. These metrics, they are handcrafted to evaluate specific properties of text. For example, the blue score measures how good is a certain translation relative to the original. There's another called rouge, which measures how good is a certain sentence in terms of being a summary of an original input. And my point is that all of these metrics are non-differentiable, and there could be other non-differentiable ways of scoring how good is the output or not. Maybe there is some general notion of reward or some general notion of score that we want to define over various discrete objects that we're generating. And in those cases, again, these classical optimization frameworks that we've discussed are not applicable because our function f could be non-differentiable. For example, these NLP scores are non-differentiable. And in those cases, we would also want to apply some kind of more general technique than the reparametrization trick to optimize problems of this form. And the reinforced trick will be one such general approach. Okay, any questions on this type of problem or the motivation behind reinforced? Okay, if not, then let's just remind ourselves what the reinforced trick is. So this is the essence of the reinforced trick in one line. Let's say that we wanted to compute the gradient of this expression relative to phi. Well, we know by the definition of the expectation that this objective can be written as a sum over different z's. That's just the definition of an expectation. And now let's say that I wanted to compute the partial derivative of this expectation relative to some parameter phi I. Let's say I wanted to compute this particular expression. Well, I can apply the definition of the sum and do a little bit of algebra to define the correct formula for this partial derivative. Because again, recall that I cannot simply change the order of the partial derivative and the expectation. That's not valid. I have to work out the correct expression with a little bit of math and algebra. So let's do that now. I want to compute this property. I know that my expectation is a sum, so I can write it as a sum. And then once it becomes a simple sum, then I can interchange the order of the sum and the partial derivative operator, which means I get this expression. So here I just applied the definition, and now I apply the partial derivative operator to my function q. So that's just plugging in the above formula into the definition of it's plugging in the first line into the second line. And now I can apply a little trick to get an expression, to get an alternative expression for the highlighted term. Here's what I'll do. I'll divide and multiply by q of phi. So this is valid because I'm just multiplying by 1, right? Q of phi divided by q of phi. But this expression has the interesting property in that this highlighted term actually equals the log. Well, it's actually the derivative of the log of q of phi. So I can write it like this, right? So this highlighted term, the derivative of log q of phi is just this. So I can do this. So far, it's just applying the definition of the log. And then what's interesting about this other term is that I now have something which looks again like an expectation. I have here a sum over different z, and each z has a weight q of z, which is a distribution. So this is just an expected value over all possible z, where the distribution is q of z, and the inside of the expected value contains the gradient of the log times f of z. So what I have derived here now is the correct way of changing the order of the expected value and the derivative operator. This is the correct way of doing this. And this little algebra trick is what we call the reinforced trick, the reinforced gradient trick. Okay, so now I have rewritten the gradient of the expected value as the expected value of a gradient. And the reason that I want to do this is because now that I have an expected value on the outside, I can approximate it using Monte Carlo like we did in all of our experiments before. Okay, so now let's use this trick and let's derive the full reinforced estimator. If I take this derivation for each partial derivative and I combine it into the full gradient, which is just the vector of all the partial derivatives, then I get the following formula, which is the reinforced formula. So similarly to how I can flip each partial derivative with the expected value, and then there's a log that there's a gradient of a log that appears inside. Here I can flip the full gradient operator, and when I flip the order inside the integrand, I now have not just f of z, but I have f of z times gradient of log of q. Okay, so this is the reinforced formula that we saw in our lecture on gradational autocores. And again, the reason why this is interesting is because after my gradient estimator is written in the form of an expected value, I can compute it approximately by applying Monte Carlo, which is the second formula. When I say applying Monte Carlo, again, what I mean is that I sample some points z1 to zk from q, and I approximate the expected value with the average over these points. And now this gives me a valid computable formula for the gradient of my objective, and I can now optimize my discrete non-differentiable objective using this formula. Okay, so this is gradient estimation using the reinforced gradient. And this is a very general trick. All that it requires is that we can take samples from the distribution Q and evaluate probabilities under the distribution. And it works for both discrete and continuous distributions. So as I mentioned, one application of this could be in discrete variable GANs. Let's say that I want to optimize this objective, then if X is discrete, so the objective for the generator is this. We want to maximize the score of a discrete GAN We want to maximize the score of the discriminator under the output of a discrete GAN. But now that Z is discrete, and I'm taking, so P of Z is my generator, right? P of G is the generator. I have to take a gradient somehow relative to this P of G. Now this becomes an instance of the above problem. So we can try applying this reinforced trick, right? Since I have an instance of this problem. So since these two highlighted terms are instances of each other, we can try to apply the reinforced trick to estimate gradients. And this is one way that people have studied for one technique that people have studied for training discrete GANs. I mean, in practice, discrete GANs are not a very successful generative modeling approach, but this is one way in which these techniques work. Another extension of this technique is, as I mentioned, training regressive models for tasks like text generation, where our goal is to optimize some downstream non-differentiable score like bleu or rouge. There, again, you have a generator, you have a non-differentiable objective. You can use the reinforced gradient estimator in the context. So, yeah, that's how it can be done. And this has connections to reinforcement learning because the reinforced trick is something that originally was created to train policy networks in reinforcement learning, if you know what that is. Effectively, you can view, you can apply this trick also in reinforcement learning, where the function Q that you're optimizing is your distribution over actions, right? So it's your policy, it's distribution over actions that you want to take in a given state, and you want to maximize the expected reward under this model, under this policy. And so the same type of optimization problem arises there, and this was the original motivation for the reinforced estimate. But you can also draw connections between the reinforcement learning setting and the generative modeling setting, in the sense that you can view your generator as a policy or as an agent whose actions are to generate tokens, generate discrete tokens or generate discrete outputs. For example, it could be generating words one at a time, and the ultimate goal is to maximize some kind of reward. Let's say you have a score for how good your generated text is or not. Therefore, this technique for reinforcement learning equally applies to training a generative model if you view the generative model as an agent whose actions are the things that it generates. So in that sense, there are close connections between reinforcement learning and generative modeling. And it even goes beyond that. There are other techniques in reinforcement learning that I haven't mentioned, which are more sophisticated ways of estimating the same gradient. So today, in practice, in reinforcement learning, folks use more sophisticated gradient estimators that reinforce, and they can similarly be applied to the problem that you see here. So they can similarly be applied to discrete generative modeling. And this is along the lines of what you may have heard of if you've been following the news or the literature on large language models. They tend to be fine-tuned using techniques from reinforcement learning, and these are similar techniques that don't use reinforce. They use another more efficient gradient estimator, but the same type of problem is solved there as well. Okay. Any questions on these applications? Okay. If not, then I would like to now go back to the reinforced gradient estimator and give you a little bit more material on that. And in particular, I want to build on what we saw in the VE lecture and add additional components to this estimator, which will make it more reliable and more effective in practice. So this is our reinforced estimator. This is our objective. This is our estimator for the gradient of this objective. And as I said earlier, this is a Monte Carlo estimate that is a function of k random samples. Therefore, that estimator is itself a random variable as a function of the random variables z1 to zk. And we can, when we view it as a random variable, we can ask ourselves, what is its expected value and what is its variance? we know that its expected value will be the correct gradient that is here. However, its variance will be non-zero. It will give us some estimate, some number that will be on average centered around the true gradient. But the spread of this estimator around the true correct value can in practice be large. This is what we mean by the gradient estimator having high variance. So even though Monte Carlo estimates of gradients are unbiased, their variance is high. And the intuition for why the variance is high is that the variance of the integrand, or the variance of the thing of which we're taking the expected value, is in practice high. If you remember the lecture the slides on Monte Carlo in lecture 4, I believe, we had a formula for the variance of a Monte Carlo estimator, and that formula was a function of the variance of the function whose value you were going to compute. And in this case, the function whose value we're trying to compute is this, whose expected value we're trying to compute is what I just highlighted on the slide. And this involves the log of a probability. In high dimensions, these probabilities can be, in practice, small. So Q of Z can be very small for certain Z's. And then when you take the log, it outputs a function that can be very close to minus infinity when this log probability is small. And so when we take logs of probabilities for small fluctuations of the probability, because the log is an asymptote at 0 that goes to minus infinity, when we have small values of Q, we're operating near that asymptote. So as a result, log of Q can have high variance, and the gradient of log of Q can have high variance. And as a result, the variance of this estimator, the variance of this estimator will also be large. So even though it will be centered at the correct value, the spread around the correct value will be very large. And so in practice, when you apply this to high dimensional Z, it doesn't work very well. It doesn't optimize your model very well. Your model will get stuck at a high value of the training objective and will not decrease. And as a result, there are many techniques for improving over the standard reinforced gradient estimator. I mentioned some more modern estimators in reinforcement learning on the last slide. So that's an entire literature, which I won't get the chance to talk about in this lecture. But there's also some standard techniques for improving reinforced estimators that I want to talk about next. And these estimators are often used in applications of generative models, which involve the reinforced estimator. Okay, so the main technique that I want to mention that can partially mitigate this problem of high variance is the technique of applying control variance. So control variance is the important concept here. What is a control variant? Let me give you first a simple example that is a simple modification to the reinforced rule, which is here. So observe that if I were to take the reinforced rule, and if I were to add any constant b here, if I were to modify the multiplier of the gradient of the log of Q by any constant, then this will not change the expected value of my reinforced gradient estimator. So for any b that I add here, it doesn't change the expected value it doesn't change this expected value. It is still correct. It still gives us what we want. Why is that the case? Here I have a very short proof. So if I have the gradient of if I have this expression, which is just the gradient of the log Q of Z times any constant b, then I can simply write out this expected value as a sum. I can take b out. I can now use the fact that Q of Z times gradient log of Z, just by the definition of the log of the derivative of the log, things simplify, and now I get an expression like this. That's the sum over Z times the gradient of Q of Z. I can swap the sum and the gradient operator because the gradient operator is a linear operator. I can do this. And now I'm taking the gradient of just the sum over all the q's, which is just equal to 1, and the gradient of 1 is 0. So for any b, this expression equals 0. Therefore, I can always add this constant b, and it doesn't change anything. It doesn't change the expected value. So it changes the variance, but it doesn't change the expected value. Right? So the Monte Carlo estimate using both this reward or using this scoring function and using this scoring function have the same expectation. However, they can have different variances. And so P is what I would call a simple example of a control variant. When you put it into your function, it can significantly improve the training of your model if you choose it carefully, because it will keep the same expected value of your gradient estimator, but it will result in a lower variance. So now let's apply. So this is the high-level idea of a control variant. I don't know if anybody has any questions on this, or if the math is straightforward, or if anybody has questions on this little derivation. I'm happy to answer questions. But if not, if you don't have questions, then I want to give you the full version of the idea of control variant in the context of this general optimization problem that we're interested in. So in its most general form, you can think of a control variant as defining a modified scoring function f hat, that is the result of the original function f, plus this extra adjustment term, which involves two things. It involves this multiplier which is similar to what I talked about, and then it involves an additional function h of z, whose expectation I happen to know, and I add this expectation here on the side. So I'm going to essentially modify the score function by two terms. One of them is a function of h of z, and the other one is this special constant, which is the expected value of h of z. So h of z will have to be something simple. I'll come back to, because we have to complete this expectation, I'll come back to what h of z should be in a moment. But this is a more general definition of the control variant. So the assumption is that we can compute the expected value, and you can easily show that the expected value of both of the gradient estimator of f and f hat is the same. Well, it's clearly the same because I'm just adding and dividing by this h of z. So I'm adding h of z, and then I'm subtracting the expected value of h of z. So if I were to take the expected value of this term, it will give me 0, because when summed over all the possible q's, this would cancel out with the expectation if I were to sum over all the possible q's as the intuition. So the value of f hat and the value of f is the same, but the Monte Carlo estimates will be different. The variance of the Monte Carlo estimates will be different. And you can see why by making one simple observation. Imagine if we took h of z to be exactly f of z. So I take a equals 1, and then I define h of z to be f of z, right? So the optimal h star, I claim, is f of z. If I were to choose this optimal h star, then in my formula, so I'm going to erase this. In this formula, if I make this choice, then these two terms cancel out. And then my optimal reward is just this. So now my Monte Carlo estimate of f hat equals exactly the expected value of h star, which is exactly the expected value of f of z, and I can get the correct estimate of my reward with one Monte Carlo sample, which means that it has variance 0, right? So if I choose this perfect control variant h star, everything cancels out, and my expectation over f hat is simply the sum over a number of terms where each term is a constant, and it equals exactly the value that I want, which is the expected value of, this becomes the expected value of Z. And because I assume that this is known, my Monte Carlo estimator has 0 variance. So in that sense, the optimal H star is the true f of Z. Now, of course, in practice, we can't choose this optimal H star, because if we could, then we would compute the expected value directly and use that. So we can't choose this H star, but it tells us that the optimal control variant is one which tries to mimic f of Z as much as possible. Okay. This is similar to how in variational inference we would choose a Q that is as similar as possible to P of Z given X, which is our true posterior. Here, our optimal control variant H star should be f of Z. So I'm going to try to craft some H which will be somehow correlated with f of Z. And if it's somehow correlated with f of Z, we will get a reduced variance for our control variant. Okay, so this is one application of control. This is one example of how a control variant might look like. And now let's use this control variant. Let's see how this control variant can be used to train a particular type of deep generative model called a belief network or a sigmoid belief network. So a sigmoid belief network is essentially a VE with a discrete latent space, right? Remember, I said that in many applications of latent variable modeling, we might be interested in having a discrete Z. Just intuitively, a lot of latent concepts in the world are not continuous, they're discrete. For example, maybe we want to know whether an object is present or not present in an image, or we want to model things like eye color or hair color. There's only a discrete number of, well, maybe you can argue with this, but there are clearly some properties that are naturally modeled by discreteness. Like how many people are present in the scene, for example. There are some discrete concepts that we want to learn, and it's more satisfying if our models can reason in terms of discrete concepts. So this is what a belief network is trying to achieve. It is a VE where the latent space is going to be discrete, and instead of assuming that Z is Gaussian, like in a regular VE, I'll assume that Z is a uniform categorical variable. Well, it's a vector of categorical variables, which means that it has some number of dimensions, and along each dimension I have one of k possible values. So this is the prior that I'm going to assume, and then everything else can stay the same as in a VE. So my decoder P of X given Z is going to be some parameterized distribution with parameters theta of psi. So theta is the parameter of the distribution over P, and psi is the parameter of the neural net that parameterizes the parameters theta, which I just highlighted. So this is going to, for example, P of X given, if X is continuous, if X is a pixel data that we can model using continuous distribution, then P of X given Z can be a Gaussian. Theta are the parameters of the Gaussian, and the parameters theta are a function of the latent discrete variables. Or if X is also discrete, then X can be if P of X given Z can be some kind of categorical distribution whose parameters are again some parameterized function of Z. So the decoder is the same as in a regular VE. And you can think of this similarly to how a VE is an infinite dimensional, it's a continuous mixture of an infinite number of Gaussians. Here you can think of a belief network as a mixture of an exponential number of Gaussians, one for each assignment to the latent variables. So how would we learn these belief networks? Because our Z's are discrete, we can't apply the reparameterization trick. Instead, we can apply the reinforced estimator, which is something that was done by this early work called Anvil from DeepMind. So this was the paper that did a lot to popularize the use of the reinforced gradient estimator for learning discrete variable models. So what the Anvil paper does is that it trains sigmoid belief networks with a modified objective where I have a scoring function f, which is the true scoring function f that I'm interested in. So in this case, we're optimizing the elbow over discrete Z. So f, my true objective, is the elbow, which is just this. And then Anvil applies that control variant that I had in my earlier slide or a very similar type of elbow. So it adds this extra term h of x and some constant b. So here h of x you can think of it as or the term that the Envil paper uses is input dependent baseline or input dependent control variant. Because my expectation is over z here, I can add any function of x, and because this is a constant in z, then this is an example, excuse me, of that discrete control, of that constant control variant that I had in my very first slide. Right, so here I have effectively added a constant with respect to z to my network, to my objective, and it doesn't change the gradient for the reason that I had on my first slide on control variance. Okay, so now this is the modified objective used by Envil, and now so I have these two control variants, constant baseline and input dependent baseline, and both of these baselines can also be learned. So I said that the optimal control variant is one that is similar to the true expected value of the thing that I'm trying to optimize. So we can learn h and b by optimizing this objective. We can train the parameters psi of h by minimizing the L2 error with respect to f, and this gives me my input dependent baseline. So I do this using training. I do this while I'm training my main networks Q and P by optimizing over phi and theta. Right? And so now the full gradient estimator for the elbow is going to be this reinforced estimator with these extra control variants. And in practice, when you train these models, this is the difference between not being able to learn a sigmoid belief network at all and getting reasonable samples on basic image data sets. So these control variants are actually needed to get the gradient estimator, to get the reinforced gradient estimator to do anything for latent dimensions greater than 16. So this is a useful tool to know. However, as I said earlier, the reinforced estimator is not the only tool that can be applied to learn discrete models. As I said, there are, in principle, more sophisticated estimators in RL, and there is also a complementary approach which tries to apply ideas from the reparametrization trig for continuous variables, which we saw in our lecture on VEs. So there's another approach which is going to try to apply these techniques to the discrete setting. This is what I want to talk about next. This is the idea of applying relaxed reparametrization tricks. So what is this idea? Again, this is the problem that we're working with. Sorry, there's a question.
I'm just curious about the control variance ideas. Were they present? What was these ideas seem very much the same as the actor-critic algorithms in RL. Is it what came first? Is it? I mean, it seems like Envil, the paper, was in 2014, but the idea of control variance is that it's kind of like a well-known idea in optimization in general, and both actor-critic methods and Envil used these ideas of reducing the variance with adding that baseline. Or was it fully an idea that was created in RL and was used for generative AI afterwards?
Yeah, that's a really interesting question. Control variants are a general idea in statistics. They're found in other areas of statistics as well. So there are, for example, control variants for importance sampling estimates. It's a more general technique than even optimization than either reinforcement learning or generative modeling. it's an idea that is decades old. Yeah, good question. Interesting question. Okay, so control variates were one approach, but as I said earlier, there is another interesting. So let's say that again we have the same optimization problem that we've been interested in, and again z is a discrete random variable. The reparameterization trick does not apply, and while the reinforcement learning trick, while the reinforced trick is applicable, in practice it is a bit of a pain to get working well, and it requires these extra patches in the sense of control variates, and these patches require careful tuning, and they require careful thinking about how to design them. It's sometimes not possible to design a good control variate, or it's really hard. So are there any other solutions? Ideally, we want to use something as simple as the reparameterization trick, where we just write our formula in a different form, and then we apply backpropagation, or we apply automatic differentiation in our favorite deep learning framework. We just get a gradient for free, and we don't even have to think about it. Unfortunately, it's not as simple when z is discrete. But what we could try to do is, when we have a discrete z, we could try to relax this discrete z into a continuous variable. And then once we have a continuous variable, then we can apply our favorite reparameterization trick. And of course, this is not going to give us the optimization problem that we want, because we're actually interested in a discrete problem. But what we could try to do is we could start with a continuous variable, and then start training with that. And over time, as we're training with our continuous relaxation, we make that relaxation more tight, and we gradually interpolate from a continuous variable to a fully discrete variable. And so at the end of training, we're going to tighten our relaxation. We're going to make z look less continuous and more discrete, and we will ultimately end up optimizing something close to what we really want. So that's going to be the idea of relaxed reparameterization tricks. And I'm going to show you one way, at least one and a half ways of one detailed example and one less detailed example of how this relaxation trick can be applied. In order to give you the first example of this trick, I will need a tool, and this tool is going to be called the Gumbel distribution. So don't worry if you've never seen the Gumbel distribution. I will give you a formula and a bit of intuition, and then I will give you one important property of the Gumbel distribution, which is the key thing that we need to know about. So first of all, what is the Gumbel distribution? Well, it's one of these distributions that is out there in statistics textbooks. This is the formula for the Gumbel distribution. Is this sometimes called the double exponential distribution? It is used in practice in applications like modeling extreme events. I'm not going to dwell too much about the intuition of these parameters. It kind of looks like a Gaussian, but we have these two exponentials. It has these like Q and beta parameters, which kind of look like the unit variance of a Gaussian. And you can control the center of the distribution. Beta can control the width of the distribution. If you were to plot the distribution, you would see things like this. So these are different densities for the Gumbel softmax, so with different values of mu and theta. And the main reason why the Gumbel distribution is interesting to us is that it can be used as part of this really non-obvious trick for sampling discrete variables. So I'm not going to prove this, but this is a really surprising fact from probability theory, which says that if we have a categorical distribution with parameters pi1 to pi k, again, we call that the categorical distribution is just a distribution over a fixed number of discrete outcomes. So it's like distribution over the outcome of a dice roll. That would be an instance of a categorical distribution, for example. So let's say I have such a categorical distribution, And let's say that I want to sample from it. There is this one really surprising and clever way of sampling from Z, which involves applying the Gumbel distribution. And it's called the Gumbel max reparametrization trick. So the way this trick works is as follows. First of all, my goal is to sample a discrete Z. I can represent any discrete variable as a one-hot encoding, right? That's just what we normally do in machine learning when we have any categorical features. So let's just say, for the sake of this derivation, that Z is a one-hot vector, and we want to sample one-hot vectors using these class probabilities pi 1, pi 2, pi 3. There is one really not obvious sampling procedure that involves the Gumbel distribution, and it works as follows. I start with my class probabilities, I take the log, and I add a Gumbel variable, a random Gumbel variable to it. So these GIs are ID Gumbel variables drawn from the unit Gumbel distribution. So I take my known log probabilities, my log pi i's, these are the class probabilities, I take their log, I add random Gumbel noise, and then I take the max, I take the argmax, and the argmax is going to be my class, the class that I claim to sample, right? So I have k numbers, I have k log pi probabilities, I randomly perturb them, so now I have k perturbed numbers. I take the largest, and the index of the largest is going to be the class that I will send, right? So for each random draw of Gumbel distributions, I have a different max, therefore I have a different category. So the max is, or the argmax, is what defines the category that I have sent, right? And then I choose my Z to be the one-hot encoding of the category that I have chosen. Does this sampling process make sense? Right, so I just start with my class probability, my class probabilities, I take their log, I add random Gumbel noise, and I pick the index of the largest noised class. This will be, the distribution of that largest index will be the same as the distribution of classes under my categorical distribution. This is the idea of the Gumbel max trick. It's a clever way of sampling from a categorical distribution. Now, why is this interesting? Why did I show you this trick? Well, observe that this formula here, it looks a lot like the reparametrization trick. I have something that's a function of the parameters of my distribution plus some random noise that's not a function of anything. This really looks like the reparametrization trick. Remember, for a Gaussian, I had mu plus epsilon times sigma, and epsilon was just random noise. Here I have log pi plus g, and g is some random noise. So effectively, what I have here is a type of reparametrization trick for categorical variables. Is there any problem that you see with the, is there any problem that you see with this trick so far? Can we apply this directly for learning generative models, or is there anything that's missing?
So I'm assuming there's going to be some like one hot argmax. These are non-differentiable operations.
Exactly. So I have a reparametrization trick, but I still have a problem. My reparametrization trick, when I view z as a function of log pi, it's reparametrized, but it's non-differentiable because I have the one-hot operator and I have the argmax operator. So this is still not fully solved because the argmax is non-differentiable with respect to pi. And this is where the relaxation idea comes in. What if instead of taking the one-hot encoding and taking the argmax, I took the softmax and I took an approximate, well, I guess the softmax will give me a vector. So what if instead of taking the argmax, I took the softmax, which will give me not an exact one-hot encoding, but a soft one-hot encoding. So what do I mean by this? So this is my non-differentiable Gumbel max sampler. Let's instead replace the argmax with the softmax to get the Gumbel softmax sampler. Right, so this is my Gumbel max sampler. It has the argmax. This is my Gumbel softmax sampler, and I have received, and Zi receives the softmax. First of all, what is the softmax? So this here is the softmax. So it's an operator that has an extra parameter called temperature, tau. So what happens here is that I have these scores, GI plus log pi. What the softmax operator does is that it takes their expected value, it adjusts, it divides the expected, sorry, not expected, it takes the x, it does e to the power of that thing, and then it normalizes and divides each x by the temperature tau, and then it normalizes so that everything sums to 1. Right? So here I have the formula for the ith component of the softmax. And the reason it's called a softmax is that this temperature interpolates between taking a hard argmax and taking a relaxation. In particular, if I were to divide by a tau that is very close to 0, or in fact, as tau goes to 0, this becomes an argmax. So when tau equals 0, all of these terms, all of these x terms, they go to infinity, but the term that is the largest goes to infinity faster than the others. And so the limit of this vector z hat when tau goes to 0 is a one-hot vector where the 1 is at the index that corresponds to the max of the inputs to the softmax. So when tau goes to 0, I get a hard max, but when tau is non-zero, I get some relaxation. I have some entries which are, so that I guess when when tau is not 0, I have a vector here. This is going to be a vector with some numbers, and these are going to be, so these will sum to 1, right? So the sum of these vectors, the sum of the entries of z hat will sum to 1, and the max will have the largest entry, but it won't be equal to 1 exactly. Right? So in other words,
sorry, on the previous slide, the tau is inside the exponential.
The tau is inside the exponential. Yeah, so yeah. This might be missing some parentheses. Okay, sorry, I'll fix this later on. But I guess, yeah, I'll this stuff for, yeah, it's missing. Okay, but my point here is that this z hat vector, it lives, so the original z's were all discrete. They were all one hot encoded. Right, so let's say this is 1, 0, 0, this is 0, 0, this one is 0, 0, 1. So let's say I have 3 classes, and these are the 3 possible vectors that correspond to these 3 classes. Now the z hat vectors will live in this space that's between them. So they will be mixtures of these different points. So basically the z hat will be a set of numbers which all sum to 1 and that live in the convex hull of the hard classes. Okay, so now my z hat will be a continuous relaxation of the hard variable z. Okay. And also the main benefit of applying a softmax is that I can now backpropagate through the softmax. I can differentiate through the softmax. So now that I have this variable z hat, I can use this variable as a continuous relaxation of the original z, and in addition, one that is fully reparameterizable. So now the idea of the Gumbel softmax trick for generative modeling is to take my original categorical sampler and replace it by the following soft sampler, which samples a variable z hat that is a continuous relaxation to the original variable z hat. Now, how does this look like in practice? Again, let's look at a few examples. So this is an example where I would like to draw from a real categorical distribution. And let's say that what you see here are the distribution of different phi i's. So if I were to take a sample from this, I will get some kind of discrete sample from, so this is going to be my discrete category that I sampled from the distribution. If I do the same thing with a reasonably low temperature, like tau equals 0.5, I will get as my output a vector where most entries will be tiny. So in particular, there will be some entries here which will be non-zero and tiny, and this big vector, or this one component, will be really close to 1, but it will not be close to 1, but it will still be large at the index of the variable that I have sampled. Right. So basically, what you have on the left is the result of applying the Gumbel max trick, and then on the right you have the result of applying the Gumbel softmax trick. And the output of the Gumbel softmax trick is a variable z hat where most entries are small, and then one entry is really large, which corresponds to the full max. I can also take this further. I can make the temperature smaller, and then you can see that these small variables have almost completely disappeared, and almost all of the weight is where my max should be. Or you can also go in the other direction. You can make the temperature larger, and if you make the temperature larger, now there's still most of the weight that's on the max category that you want to sample, but the z hat variable also has a lot of non-zero components in the other dimensions, and they're larger. And if you make your temperature too large, then the output z hat from the continuous sampler will not look like anything at all. It will just be a uniform distribution, because now you have chosen a temperature that is too high. This is how this thing approximates different distributions, right? So again, as tau equals 0, we have samples from a categorical distribution. And so what we could try to do now is to plug in the z hat directly into the elbow, for example, and try to optimize this function. The advantage of this is that if we have a small enough temperature, we will almost get a categorical variable, which means we will almost be optimized for what we want. Now, the problem is that if we make our tau too small, then we will almost have a discrete variable. And if we want to try to backpropagate to something that is almost an undifferentiable argmax, our gradients will be very large, and as a result, the gradient estimator will have high variance. And so in practice, what you want to, and of course, the other problem is that if the temperature is too large, then our gradient estimators will have low variance, but we will be sampling from a different distribution and one that and so in practice, what we will do is we will interpolate tau over the course of learning, and we will start with some very diffuse z hat and gradually make them tighter, gradually make the temperature smaller, make the approximation tighter, and as a result, it can work quite well. Right? This is again this geometric interpretation that I showed you earlier. Imagine we had three possible classes, then the z hat lives in the simplex or in the convex hull of the three hard classes. And you can view the distribution as placing weight with, you can view the tau as determining where to place weights within the simplex. If tau is very small, or if tau is 0, and you have the categorical distribution, then all of the probability mass lives only in these three endpoints. But if we were to increase the temperature, then this blue region shows the parts of the input space where the z hat are allowed to live. So if you increase tau, then you allow the sampling of points close to the edges, but within the simplex. If you make tau really large, most of your points will be within the simplex. All right, and so here, let's look at an application of Gumbel softmax. One way to apply one place where Gumbel softmax can be applied is in these sigmoid belief networks, which I showed you a few moments ago when I defined when I was giving an example of the reinforced estimator. So let's say that now we want to solve an elbow. Let's say f of z is the elbow. What we could do is we could replace z by z hat, and then gradually anneal the temperature during learning. Now, one note here is that in practice, we have to have an f which supports discrete approximations. So we have to have which supports continuous approximations. So f has to support some continuous z hat. For some f, it might not be defined for a relaxation of z hat. So this only works with objectives that are defined over a continuous relaxation. If it's not defined, then we can apply the discretization step in the forward pass and still perform this green, and still use the same green estimator in the backwards pass. This would be a certain type of approximation known as the straight through green estimator, which you can look it up, or I can tell you more after the lecture. Okay, and so what is the result of applying all of this? Also here, these are some examples of the elbow as a function of time for various gradient estimators. So for some of these estimators, I guess here I am looking for, this doesn't even have, so I think, so essentially these are two versions of the softmax estimator, and then everything else. I think some of these should be really similar to reinforce, and some of these are instances of this straight-through estimator that I mentioned. But essentially, in practice, the Gumbel softmax trick works quite well, and it's also quite easy to implement. You can just apply, you can just plug in that formula directly into PyTorch or your favorite framework, and then run the forward pass. You get the grades for free in the backward pass for any choice of temperature. So in practice, it's really easy. So this is the Gumbel softmax trick, and I'll just conclude briefly by saying that actually this idea that I just described is much more general than just the idea of parameterizing discrete variables. There's a lot of other objects that we might be interested in. For example, there's a lot of other discrete objects that we might want to try to model. For example, permutations could be another object, or maybe latent syntax trees are another discrete object we want to model. And in fact, for most of these discrete categories, trees, graphs, permutations, all of these discrete objects tend to admit a relaxed reparametrization trick that can be used to obtain gradient estimators for these stochastic optimization problems when z is that type of variable. Okay, so just an example here for permutations is something called the Plackett-Luce distribution. So the Plackett-Luce distribution can be thought of as an extension of the categorical distribution to permutation. Similarly to how the categorical distribution is a distribution over fixed classes over categorical variables, the Blackett-Luce distribution is a distribution over permutations, and we might want to sample from permutations as well, right? So there is a relaxation of the Blackett-Luce distribution, or no, sorry, there is a sampling trick. There is a reparameterized sampler for the Blackett-Luce distribution, where we also perturb the scores of each element using Gumbel noise, and then we apply a sort operator, and we can obtain a discrete permutation out of that. Again, this is reparameterized, but not differentiable, and similarly to how the softmax can relax that hard differentiation step, how it can lead to a differentiable approximation to a non-differentiable objective. There is a similar relaxation that can be applied here to the Blackett-Luce distribution. Okay, so I'll just summarize all of this by saying that discrete latent variables can be even thought of as its own special topic within generative modeling. Discreteness is found in many places, either the things we're trying to model or in latent space, and it has its own set of challenges. I've just mentioned two important tricks in generative modeling that address some of these challenges, and there's many more. There's an entire literature on this. So if you're working with any of this for your own projects, I encourage you to talk to me, and I can point you to more. You can start with these ideas, and I can point you to more directions for other